Hi guys. So now today I'm going to start a new topic, right, called capacitors. Now if you look at any old radio set, right? I mean nowadays you don't see those. Like you will see those cylindrical devices, right? And you must be wondering, like what is there inside, right? So some of them, right? Some of those devices are capacitors, and now today I'm going to kind of give you the very basic idea behind what are capacitors and why do we need capacitors, right? Now we have talked about charges in electrostatics, right? Now there are scenarios. I'll not talk about what those are. So there are scenarios where, let us say, when designing certain circuits, we want to store charges and to make them flow sometimes. So let us say what I require is, our requirement might be that, okay, we store some charge, right? We store some charges, right? And under some circumstances, right, I would like, let's say I want to store some positive charge, some negative charge, and I might want charge to temporarily to flow from here to here, right, for let's say a short period of time. Right? Why do we need it? Don't worry about it. There are in electronic circuits and there are many applications where we require this kind of thing. Okay, so we want charges to be plus and positive and minus charges to be separated, and we want them to be able to flow. That will look like, yeah, it's pretty obvious. So like let's do that. But how do you do that? If you take any material, right? I can take a pen, I can take human body, or take anything, right? It is electrically neutral. Any atom on generally, right, will have the same number of positive and negative charges. So the charges inside the nucleus is same as the charges in the electrons. So it's electrically neutral, right? So it's actually it's not that trivial, right? So now how do you separate these charges and how do you kind of make them flow, and we'll talk more about how do you make them flow in a certain manner, right? That'll come later, right? Now if you want to do this, let me give you an analogy. So let us say somebody told you, like you want to have a mechanism whereby you make water flow in a pipe from here to here. So we'll say, okay, fine, that's not very hard. What will you do? You will, let's say I take a tank, right? I take a tank and I fill it with water, right? So this is, let's say, water, and then from here there is a pipe, right? And then the pipe is connected to, let us say, another tank, right? And this tank is empty and this is full of water. What will happen? When you connect with this, when you open this, right, then water will start flowing, it will come down. So, and then gradually the water will reduce and it will start filling up, right? So what did we do here? First thing, notice first thing. First thing is we stored some water, right? So we stored some water, and the more water you want to flow, the bigger capacity tank you are going to use, right? So now the question comes, how much water can you store? Or in other words, what is the capacity of this tank, right? Second thing you notice, we kept one at a higher level, one at a lower level, right? Now in terms of gravitational potential, you would say, oh, this had more potential energy, right? This had a lower potential energy, right? Now when we want to store charges, we could do something very similar, right? So now how do you do that? So here in this case, right? In this case, there was some mechanism to take water and pour it into this tank at a higher level. Now who will go and how do we get charges to, let's say, this charges to be taken from this and move to this point, right? Which gadget or which device or what object do you know which can move charges? Battery, right? Okay, so now let's look at what a battery does. What's a battery? So battery is essentially, let us say, I'm just going to draw this cylinder kind of thing, right? So think of any torch battery or any kind of AA, AAA battery. So it will have what we'll call a positive side. It will have a negative side. And what does the battery do? Inside the battery, visualize it, right? Visualize as if there was a guy inside. There's no guy. Don't start breaking batteries and looking for a guy inside. Okay, there's no guy, but let's say there's a guy inside, right? And this guy, what he do is he would take some plus charges and he would move it from here to here. This is the guy's job, right? Now in reality, what is the guy inside a battery? It is the chemical, right? There is some chemical filled inside and there is a chemical reaction, and that chemical reaction will take the positive charge and push it towards this terminal, right? So in the end, what will happen is you will have one terminal which will have a higher potential and this will have a lower potential. Okay? Remember, when there are more positive charges, it is at a higher potential, right? Now, can I use this, right? Can I use battery to kind of create this kind of charge separation? Yes, we can. How? Very simple. So let's say if I take this battery, right? Now I'll draw a fresh battery because there's a guy inside and this will confuse you. There's no real guy there, okay? So let's say now there is a battery here, right? And this is the positive, this is the negative terminal, right? And now and they're positive and negative, there will be some potential difference, right? Could be, let's say, 3 volts, 6 volts, 12 volts, doesn't matter. Let's say there's some potential difference, right? Let's call it V, right? Potential difference between these two terminals, okay. Now if I connect it, let's say connect them to some separate conductors, right? So I connect this to, let us say, some conductor, and I connect this to, let's say, another piece of conductor, right? Now why conductor? And so there are two things here. So one is we want to store charges. So charges have to be, in some object, right? In some body. Second thing is we want charges to be able to flow, right? So I want to be able to connect them and make charges flow. So I'm taking two conductors, right? Now when I connect, what will happen? Think very carefully, right? What will happen? Now this is at a higher potential, right? Why? Because there is some chemical reaction inside which is, trying to push the charges. So it will cause some charge to flow from here to here, and as a result this will end up having some positive charge, and this piece of metal would end up having some negative charge. Okay. Now why is this going to get positive charge? So this is at a higher potential. Now when you bring it initially, right, so this didn't have any charge, so let's say it was zero potential. Now this is high potential, this zero potential. What will happen? Charge will flow. Once again, the battery, this terminal is at a higher potential, right? This is at zero potential, this has got some positive potential. When you bring it together, then some charge will flow, right? So, and where is the charge coming from? The battery was neutral. Remember, the battery was electrically neutral. There was no net charge, right? These two also were electrically neutral. There was no charge here before we connected. So charge cannot be created and destroyed, which means total charge has to be zero, which means if there is some plus charge here, there has to be some minus charge, which means essentially the electrons were pulled from here and they were sent to this particular conductor, right? Now this will be at a higher potential because this and this, they are at the same potential. Remember, if this terminal and this object, they were not at the same potential, what would happen? There would be electric field and current would start flowing, right? But we are talking about a situation where it's in a steady state. So this will be at a higher potential, this will be at a lower potential. Let's say potential of this is, I call it V plus, and potential of this I call it V minus. Sorry, not V1, this is V minus, okay? So this is V plus and this is V minus, right? And what will be the potential difference? V. This has got same potential as this and this has got same potential as the negative terminal. So this difference is V, so this difference also has to be V. So which means V plus minus V minus is equal to V. Right? Now this V we would call, so now let's now start using some let's get some terminology, right? So here now these two set of conductors, right, they can store charge. They have a capacity to store charge, and hence this combination we'll call it a capacitor. So capacitor is nothing but it's a set of two metals, and they can be any shape. We'll talk more about it, right? And when we connect them to a battery, one of them will have positive, one of them have negative charges, right? And they can store some charge. So this arrangement is what we call a capacitor. Okay? And how much charge can they store? What's the total charge? If the charge here was, let us say, plus Q, right? What is the charge here? Charge here would be minus Q. Why? Because the total charge is zero. Remember, there was no charge before we started. So this is minus Q. Net charge is zero, but we call plus Q as a charge on the capacitor. So plus Q, this would be called the charge on the capacitor. Okay? So that is number one. Second, remember, plus Q and minus Q total, that is not the charge. Plus Q and minus Q total would be zero, right? We are saying only the charge. We take one of them. We'll say this is the charge on the capacitor, and we'll say the potential, right? The potential of the capacitor is what? It is V plus minus, sorry, this is not V1 again. Sorry, I made a mistake. This is V minus, right? So V plus minus V minus, right? So this is going to be the potential. Now one last thing here, right? What would be the relationship between V and Q? V and Q. What would be the relationship? So as an example, let's say for the same conductor, instead of a battery of 1.5 volts, let's say I took a 3 volt battery or a 12 volt battery, what would happen to the charge here, right? Now I'll just tell you and I'll give you the intuition behind it. Now we'll find that the Q, the charge, right, is going to be proportional to V. The charge is going to be proportional to V. Why is that? The intuition, the logic behind that is, remember what causes potential? Charge, right? And for a, let's say if you take a spherical conductor or any spherical object uniformly charged, the potential was what? Potential was VKQ upon R. Or if you take a point charge also, even better, let's take a point charge. So this is also Q, or you can take a conductor, this is Q, right? Plus Q. Take this point charge. For this, what is the potential at any point? This KQ upon R. So if I take a point at distance R from here, KQ upon R, right? Now let us say instead of one Q, there were, let's say, Q1, Q2, Q3, Q4, right? Q1, there is another Q2 and so on. What would be the total potential? It will be total potential, V total, right? V total would be, right, V1 plus V2 and so on, right? If there are multiple charges, one Q1, there is one Q2 and there is Q3 and so on. So essentially it will be the total potential would be the V1 plus V2 plus V3, the potential, sum of potential of each of the charges, right? Now what do you notice? Charge of each of the potential, right? For each charge, the V and Q, they are proportional, right? So now let's say there are a bunch of charges here. The potential of this is a result of potential of each one of them, each of the charges. Now if you double each charge, what happens? The total Q would double. If the Q is double, imagine that each point charge we are doubling it, right? Which means my V also will double, right? Remember, V is proportional to Q, right? You're adding up all these, when you start doubling each charge, each of them would double, sum total also would double, right? Which means V is proportional to Q. That's what you're saying. And one final thing, right? When we have an equation of the form A is proportional to B, whenever we have a relationship, a mathematical relationship which says that A is proportional to B, we can say that A is equal to some constant into B, right? So here I can say Q is equal to some constant into V, and that constant we'll call C. Right? The C is some constant. And what is C? C is nothing but Q upon V. Right? Now what is this telling me? This is telling me, right, that that higher is the C. Think carefully. Higher is the C, for the same voltage Q would be higher. Right? Higher is the C, for the same voltage Q is higher, which means C is more, Q is more, which means if the capacity is more, it can store more charge, which means C indicates if C is more, capacity is more, and therefore we call C as the capacitance. So C is called capacitance. Okay? And one final thing, right? What is the unit? Unit of capacitance would be 1 unit of charge divided by 1 unit of potential. So what is this? The unit of capacitance is going to be its unit, right? Its unit would be what? It would be, charge would be coulomb, right? And this would be volt, right? So it will be 1 coulomb per volt. Right? So this is going to be the unit of capacitance, and we call this, we give it a name, we call it farad, F-A-R-A-D, right? So I'll write this here in summary, right? So we'll say 1 farad, 1 F, right? This is equal to 1 coulomb, right, per volt. This is named after Faraday, right, the famous scientist. So 1 farad is equal to 1 coulomb per volt, right? So this is the basic, and now we'll build on this in the coming video. Thank you.